Okay, so a third possible way of representing a line in 3 dimensions is a vector equation of a line. So here's what we do. So same idea. I've got a vector, ABC. Well, here's what we do. And a point. So let's let our 0 vector be that vector through that point, initial point, x0, y0, z0, or the given point, I should say. X, Y, Z. All right. So we've got this point up here, wherever it is on our line. Okay. X0, Y0, Z0. So what we're saying is, let's make a vector to that point. That's going to be R0. Okay? Now, R, so this is, so we've got this, the other stuff on here, vector V is, let's say that's our direction, so that's vector V. And so our line is going like that. So it's parallel to that. It's more like that. Design this the best way I could, but it's parallel to that off here into space. So that's our vector B. But anyway, this is our zeros to that given point. That's what our zero is. R, on the other hand, just vector R, that's going to be the vector out to this arbitrary point on the line, call it X, Y, Z. R is that vector to that, so just label that as X, Y, from the origin. So that's vector R. Okay? Well, here's what we know then. This is where the equation comes from. By vector addition, R equals, so this R right here, it would be this vector, R0, plus this vector from here to here, which, it's parallel to V, so it's adding some multiple of V to that, call it T. Whoops. So R, would you agree with me, is R0 plus some multiple of vector V. V is just the direction given along with that point. Well, plugging in those components, if you will. So R0 is just the X0, Z0, Y0 vector. And then, V is just the given vector. ABC. R is just going to be whatever those two are added together. TA or AT, Y0 plus TB, Z0 plus TC. Okay. So this, for some reason I might, they might even just list it that way. That's vector form of a vector equation of a line. Here or here. So again, you got the same through x0, y0, z0, parallel to vector b. So you're still in the same two things, point and vector. Just another way of listening a lot. But of course, you know, it is given it in vector form. So what this one does is to get the line out of this thing. Notice how the line is established here. The line is by taking the end points, if you will, the terminal points of each of these vectors, right? Because that's how I sketch out this line. So I go here, and then the next XYZ would be out here, and then the next XYZ would be out here. So it's just giving it a different form. Instead of giving it by point, you're giving it in terms of a vector. It's the terminal, the tip of the R vector there. So it's a little different. May not be as familiar to us, but we'll talk more about vector functions as we go along here, but this is one example. Vector equation of line. So, yeah, so it's real straightforward, I think. I mean, other ones to give you except is this the same? Yeah. So say the vector equation of the line through 2, 3, 1 parallel to b equals -165. So it says R equals R0 plus T times B. That's probably the easier way to remember it. And R0 is just the vector made out of that point, 2, 3, 1. And so R is 2, 3, 1 plus T times B, -165. So if we add again, to add those two vectors, you're just adding the components, right? So it'd be 2 minus T, 3 plus 6T, and then 1 plus 5T. Somewhat similar, just in a little different format there. All right. Now, one question let's talk about here is in 2 dimensions, sometimes we talked about parallel lines, and sometimes we talked about perpendicular lines. Well, when we go to 3 dimensions, it adds a third component to that. Well, parallel intersecting. You could have parallel or intersecting lines. That's the 2 options in 2 dimensions. They're either parallel or they intersect, which they could intersect at right angles, be perpendicular, but there is a third possibility when you go to 3 dimensions. When you go to 3 dimensions, you can have parallel lines, you could have intersecting lines, but you could also have skew lines. And the best example of skew lines is take a look at the corners of any room. And so along the bottom here of the wall here, if we took that line in the corner and then the line on the ceiling, those would be parallel. If we took a line that's on the in the corner of the room and with a line that's on the ceiling or the floor there, those would be intersecting. However, what if we had a line here along the this wall here, and then we had another line that goes along that ceiling line? Would those lines be parallel? One's this way and one's this way. Would they intersect? No, because one's down here and one's up here. That's an example of skew lines. So there is a third option when you have 3 dimensions for lines. It could be parallel, it could be intersecting or skew, or think of a box, the corners of a box, the lines there. So anyway, parallel, intersecting, or skew. So skew lines are those lines that aren't parallel, that aren't intersecting either. So it's kind of interesting to think about those possibilities. So how do we do this then? How do we determine if we've got which one we've got here? Well, let's say we've got 2 lines in 3 dimensions. X equals 2 plus t. Y equals 8 minus 3t. Sorry, 6 minus 8t. And then z equals 4 minus 3t. That's line 1. And then line 2 is x minus 5 over negative 1 equals y minus 2 over negative 2. And then z minus 5 over negative 2. So that's the question. Are those parallel? Are those intersecting? Or are those skew? Well, I'll just tell you this. The way you figure out that if they're skew or not is if they're not parallel and if they're not intersecting, okay? So skew lines, I don't know, by basic definition you could say, they're just lines that aren't parallel and that aren't intersecting. So if I can figure out these aren't parallel, or if I can figure out these aren't, and if I can figure out these aren't intersecting, then they've got to be skew lines. Parallel is probably the easiest one in 3 dimensions to determine here, so let's work on that. Are these parallel? Well, if we think about it, what these 2 lines represent is basically they represent a point and a vector, right? Like here, I've got the point 2, 6, 4, and then the vector is 1, negative 8, negative 3, right? If you kind of backtrack. And there's other points we could get, but that's our parallel vector, and let's call it V1. So V1 would be the vector 1, negative 8, negative 3. That's kind of our direction vector. That we know that line is parallel to that vector. Now this one's in a little different format here, well, what's the vector here? Well, the vector components, if you will, of this one would be the ones down here, wouldn't it?
Yeah.
The vector here, because think about it again, t equals x minus 5 with a negative 1, so that's going to be negative t equals x minus 5, x equals 5 minus t. And so the vector part of that is going to be, if it's set up like that, that's going to be the vector part of it. So it's v2, the direction vector, would be the denominators there. Now, from those two vectors, I can tell here whether or not these are parallel. Because if these are going to be parallel, then one vector is a multiple of the other vector, right? Vice versa. But to be parallel, the two direction vectors would have to be multiples of one another. One is a multiple of the other, vice versa. Is that going to be, am I going to have both? Well, I can multiply that one by negative 1, so that possibly, but that ain't going to work there, is it? You're going to take, that's a 4. In other words, it's got to be a constant multiple. You see what I'm saying? That's not going to work here. There's no way to get 1, negative 8, negative 3 equal to some multiple of negative 1, negative 2, negative 2. It's not going to happen. It's just not going to work out because they're not the same multiples across the board there. So they're not parallel. What about intersecting? Well, intersecting is a little different. Intersecting means they have an intersecting point. They have a common x, y, z. All right, and so that's where, in this case, here's what we're going to do. All right, so here's where we're going to set it up. I'm going to say, you know, our parameter that we chose was t, has been t, but as we saw, you know, these, well, to get a common x, y, z here, I'm probably going to have to use a different value of a parameter than I would have to here. So here's what I'm saying. Instead of using t for this one, let's use s, and then we can set up a system. So we're going to have, for line 1, we're going to have 2 plus x equals 2 plus t. Y equals 6 minus 8t. And then z equals 4 minus 3t. For line 2, however, yeah, I'm going to put it back in the parametric form, but I'm going to use s instead of t here because, yeah, the parameters don't have to be the same, it's just the x, y, and z here. So, what do we say? So x would be 5 minus s. Use s instead of t for that parameter. Or you can use t1 and t2, I guess. Maybe that would probably make more sense. But anyway, what would the y be? Well, let's see. So we'll use s. S equals y minus 2, negative 2. So that's negative 2s equals y minus 2. So 2 minus 2s is the y, and then the z. 5 minus 2. So here's what you can do with kind of treat it as a system here. Is there a solution, X, Y, Z, a common X, Y, Z solution here? Well, for example here, I picked, all right, so I've got 6 minus 8t equals 2 minus 2s then. And then I've got 4 minus 3t equals 5 minus 2s. So if I look at that system, yeah, I think it's solvable here. Bring that over here. Easier to see. Yeah, if I just multiply this one by -1, let's see. 6 minus 8t equals 2 minus 2s. -4 plus 3t equals -5 plus 2s. That'll get rid of the s's. Positive 2 minus 5t equals -3. Subtract -5t. So that's going to be t equals 1, which would mean 6 minus 8, plug in the 1 would be t. 6 minus 8 equals 2 minus 2s, so that would be what? S is 2. Okay, so t equals 1, s equals 2 would give me the same yz value. I'd have to check that in the x's though. So these give me the same x, these give me the same y and z values. Right? X is 1, S is 2. So the y value would be, what would the y value be? 6 minus 8, -2. Yeah. And then 2 minus 2 is -2. And then 4 minus 3 is -1. And then 5 minus 4 is 1. Yeah, that's right. So they give me both the same y and z value. Is that true for x? Because it just works on the y's and z's, it doesn't give me the same x's, that doesn't work. All right, so x, so I've got t equals 1, so that'd be x equals 2 plus 1, that would be 3. That's line 1. Line 2, x would be 5 minus s, so it'd be 5 minus 2 and 3. So sure enough. So if you solve a system out like that, and you get the same x, y, z value, so I've got line 1 and line 2 have the exact same x, y, z values. So what that means is, yeah, line 1 and line 2 intersect. So, we said parallel one's a whole lot easier than it is for the intersecting. And then the skew one, I guess that's an easy one too, because if they're not parallel, they're not intersecting, then it's skew. So that's how you tell if it's skew or not. That's the only other option. It's got to be one of those three. Is that all right? Any question or concern with that?